Good morning, everyone. Today, I'm going to talk about estimation of high-dimensional change points under a group sparsity structure. So first of all, what are the change points? So change points are time points at which abrupt changes occur. By estimating the location of change points, we can split the time series into shorter segments where that can be analyzed using the method designed for stationary time series. So existing univariate change point method include these three kinds. So top-down method like wide boundary segmentation, method through the penalization like prone exact linear time method, and the last one is the multi-scale test like the simultaneous multi-scale change point estimator. However, these methods are inadequate for the high-dimensional change point estimation. So high-dimensional change points estimation are based on so-called Q-sum transformation, which I will give a formal definition later. So some high-dimensional change point estimation procedure include L2 or L infinity aggregation, which is basically to aggregate the column-wise L2 or L infinity norm of the Q-sum transformation of the data matrix, and double Q-sum algorithm. After applying Q-sum transformation to the data matrix, we then apply a second Q-sum transformation to the sorted columns of the Q-sum matrix. Another type is the projection-based algorithm. For example, inspect algorithm by Wang and Samuels in 2018. So for projection-based algorithm, we first want to seek optimal direction of projection. And then we project our data matrix along this direction to get a one-dimensional data series. And then we use the one-dimensional change point estimation procedure to locate the change points. So in high-dimensional change point estimation procedures, sparsity is often taken as an assumption. So sparsity assumption can greatly reduce the complexity of the original problem, but it often does not capture the full extent of the structure of the vector of change available in real data application. So in many applications, it is natural to assume that the coordinates can be clustered into groups, and the coordinates within the same group tend to change together. So example includes the financial data stream, where changes are often grouped by industry sectors, and a small number of sectors may experience simultaneous market shocks. And my research objective is to propose change point estimation procedure on the group sparsity structure. And our proposed method is also a projection-based algorithm. So the group sparsity structure here means that we can divide the coordinates into several groups. And the changes will only occur in a small subset of the groups, and the coordinates within the same group tend to change together. Now, let's look at the problem description. We assume that the data is generated like this. So xt follows the normal distribution with mean mu t and covariance matrix sigma. And we assume that the operator norm of the sigma is less than or equal to some positive number b. And we assume that the mean vector undergoes changes at time z1 up to z nu in the sense like this. We assume that z0 is 0 and z nu plus 1 is n. And then we can divide the p coordinates into g groups. We use jg to denote the set of indices associated with the jth group. we will consider both the non-overlapping group and overlapped group case. And in the case when the groups are non-overlapped, the JG here forms a partition of the set P. Now let's look at the assumptions. So first, we assume that the spacing between the change points satisfies this inequality here. And then before we state our sparsity assumption, we first define the vector of change theta I to be mu I minus 1. And then we define a function phi, which maps a p-dimensional vector to a g-dimensional vector. So phi x here basically is to summarize the coordinates in each group by the L2 norm. And now we can state our sparsity assumptions. So we assume that the total number of coordinates with change is less than or equal to k. The total number of groups with change is less than or equal to s. And the magnitude of change is greater than var theta. And our goal is to estimate the location of, our goal is to estimate the location of change Z1 up to Z new from the data matrix X and the pre-specified grouping information JG. Our general idea is to first start by considering estimating a single change point, and then we combine it with a top-down method to locate the multiple change points. To estimate a single change point, we first need to seek a direction V hat, which is close to the direction of change. And then we project our data along this direction, and then use a one-dimensional change point estimation procedure to locate the change points. Then how can we do it? So we first introduce the Q-sum transformation of the data. For a specific row at time t, the Q-sum transformation is defined in this way. So basically, for a fixed t, we are calculating the mean to the right minus the mean to the left, and then scale the variance to be identical. And then, because our method is a projection-based method, so our goal first is to find optimal direction of projection. If we have the full knowledge of the data generating mechanism, the ideal projection direction is the vector of change because it is an optimal way to aggregating the signals. However, we actually do not know it, so we need to use the sparse version of the Q-sum matrix T to estimate our projection direction. So initially, we want to solve this optimization problem subject to this constraint. However, we can see that this problem is non-convex, so actually it is very hard to solve this problem. Then we want to perform a convex reduction of this problem. So the problem in the first line is the initial problem that we want to solve. And we note that the maximum of the L2 norm of U transpose T can be written as the maximum of U transpose T times unit vector W, which is a n-dimensional unit vector. And then the maximum of U transpose T W can be written as the maximum of the trace of the TW times U transpose. And the trace of the TW U transpose can be written as the inner product of the UW transpose with T. And then we write the UW transpose as the matrix M. So then the problem can also be expressed in this way. So So then this becomes a matrix optimization problem, and the matrix M here should satisfy this constraint. And then we drop the rank constraint and replace the nuclear norm constraint with a larger Frobenius norm set S here. And the group sparsity constraint is summarized in the penalty here. Now we define a new norm, which is called the group norm. So for group norm, basically we first want to split the matrix M into several blocks according to their grouping information. And then we sum over the 2-1 norm of each block times the square root of the group size. And the 2-1 norm here is the column is the sum of the column-wise L2 norm within each block. So then we only need to solve this convex relation version of the original problem. After we obtain an optimizer M hat here, we can extract V hat by finding the leading left singular vector of the M hat. And after obtain this projection direction, we then project the data along V hat into a one-dimensional time series, and then apply a one-dimensional change point estimation method to locate the change point. Then how can we solve the relaxed convex problem? We have shown that when the groups are non-overlapped, there is a closed form solution for the optimization problem, which is stated here. And if the groups are overlapped, we then use Frank-Wolf algorithm. So Frank-Wolf algorithm, basically we are performing a gradient descent on a convex constraint set. So the whole algorithm is summarized here. We input with the Q-sum matrix, the grouping information, a tuning parameter lambda, and a threshold epsilon. We initialize the M hat with T over the Frobenius norm of T. And in each step, we first calculate the gradient of the gradient of the optimization problem. And then we update the optimizer M with a linear combination of the current point and a point on the sphere, which is proportional to the current point. And after that, we project this point back to the sphere S. And when the M hat I plus the Frobenius norm of M hat I plus 1 minus M hat I is smaller than a certain level, then we output the M hat I as the optimizer. Then here is the whole procedure for a single change point estimation. So we input with the data matrix X, the grouping information GG, and a tuning parameter lambda. We first calculate the Q-sum transformation of the data X, and then we solve this optimization problem using either closed form solution if the groups are not overlapped, or the Frank-Wolf algorithm. And then we extract V hat from the optimizer M hat. And then we locate the change point by finding the maximum Q-sum statistic of the projected series. So this is the whole algorithm for the single change point estimation. And then we combine the single change point estimation procedure with the top-down method called wide binary segmentation to locate multiple change points. So again, we input the algorithm with the data matrix X, a grouping GG, a tuning parameter lambda, a threshold, and a threshold QC. So we initially draw a number of intervals from this set. And for each of these intervals, we will perform a single change point estimation stated before. And for each interval, we will return a candidate change point and the associated maximum Q-sum statistics. And then we compare all the Q-sum statistics from all the intervals and choose one which has the maximum value of the Q-sum statistics. And if this maximum Q-sum statistics is above a certain threshold C, then we admit the corresponding change point as a true change point. And then we split the data series from this point and repeat the same process for the left-hand side and the right-hand side. So this is the overall algorithm for the multiple change point estimation. Then we also provided some theoretical guarantees for our change point estimation procedure. So first, let's look at the theoretical results on the projection direction. So theorem 1 is the upper bound for the sine angle loss between the estimated projection of direction and the oracle projection direction. So for a given group in GG, we let P star to be the minimum group size. And we suppose that coordinate J belongs to at most C groups. And for this theoretic choice of tuning parameter lambda, we have that with a probability at least 1 minus 1 over NG that the sine angle loss between V hat and V has this order. So if we have that all the groups have the comparable size, then K over P star here is the group sparsity, so which is the number of groups with change. And we can see that the upper bound here undergoes a phase transition as the P star increases above a log Gn level. And if the P star is large, we expect that the sine angle loss, so when P star is large, we expect the first term K here to be the dominant term of the sine angle loss. And in this case, the loss has minimal dependence on the P star here. And then we look at the lower bound result for the loss of the projection direction. So suppose that the groups are not overlapping, and if these conditions are held, and we denote these things as the order statistic of P1 up to PG, and we denote this as the minimum value of sigma. Then for some universal constant C, we have that this lower bound is satisfied, and the infimum is taken over the set of all measurable functions V hat of the data X. So this theorem shows that the phase transition obtained in the previous theorem is not due to specific proof techniques, but it is an intrinsic feature of the problem. So if we look at the terms here and look back at the terms in the theorem 1, so we can see that the terms in the lower bound matches with the terms in the upper bound. And the term K here comes from the case when we know the grouping information. In this case, we have in total K parameters. And the J over S comes from the case when we do not know the group information. And in this case, we have in total J choose S possible models. And finally, let's look at the theoretical results on the estimated change point location. We note that the V hat, which is the estimated direction of change, has dependence on the Q sum matrix T. While this dependence is observed to be weak in practice, it creates difficulties for our theoretical analysis. Therefore, we may want to work with a sample splitting version of the original algorithm. So if we look back at our algorithm 2 here, so before we are using the whole data matrix X to both estimate the direction of change and then project the data alone. But now we want to split the data matrix X into 2 parts. So we split the X with the odd columns and the even columns. And then we use the odd columns to estimate the V hat, and then use the even columns to project the data along the V hat estimated by the odd columns. And by working with this sample splitting version of the algorithm, we can have this theorem. So we let that hat be the output from the sample splitting version of algorithm 2 with this choice of tuning parameter lambda. Then there exists universal constant C prime such that if n greater than 12 and is even, and that is also even, and if this condition holds, we can have that with high probability that 1 over n times the absolute value of that hat minus that is smaller than or equal to a constant times b log n over n var theta squared. So this is our theoretic result for the overall change point estimation procedure. We also did some simulation studies for our method. So the first part, we want to validate our theorem 1. In these simulation studies, we assume that all the groups have the same size. So the P star here is the group size, and which is the elements per group in the x-axis. We run the algorithm for 100 repetitions, and each time we can get estimated projection direction. And for each estimated projection direction of projection, we calculate the sine angle loss of V hat. We calculate the sine angle loss between V hat and the oracle direction of projection V, and we plot it against the elements per group. We conduct the experiment in 2 settings. So we first look at the left panel. In the left panel, we fix that the total number of coordinates with change to be 60. And because the group size is varying, so the group sparsity is also varying. And for the right panel, we fix the group sparsity to be 3. And we the total number of changes with the total number of coordinates with change is varying with P star. So in both these 2 settings, we run the simulation for different P values and different signal values. So S in the legend here is the signal size, but S in the caption is the group sparsity. So we first look at the plot on the left panel. We can see that the loss initially decreases linearly with the elements per group P star and turns to plateauing eventually. So if we look back at our theorem again, for small P star, the second term here is the dominant term of the sine angle loss, and the loss decreases at a rate approximately proportional to 1 over square root of P star. And if P star is large, then the first term is the dominant term. and the loss has the minimal minimal dependence on the P star. And if we look back at the plot here, we can see that this simulation result matches with our theorem 1. And then we look at the plot on the right panel. So we can see that the loss increases with the elements per group P star. And also in this case, the first term in the sine angle loss, which is term K, is the dominant term. And so the average loss increases linearly with the element per group at a log-log scale. So this also matches with our theory. Then we want to compare the performance of our algorithm with another projection-based algorithm inspect, which only takes the sparsity as the assumption, but without considering the group information. So groupInspect is the name of our algorithm, and inspect is the algorithm we want to compare with. So we also conduct the simulation experiment under 2 settings. So on the left-hand side is the settings when the groups are not overlapped, and the right-hand side is the setting when the group is overlapped. So we also compare the sine theta loss obtained from these 2 algorithms. So from the so we plot the sine angle loss against the log2 scale of the signal size. And from the plot, we can see that in general, the groupInspect can have a better performance than the inspect algorithm. So, and if we look at the plot on the left, we can see that the groupInspect can achieve a good performance even when the signal size is small. And then we also compare our algorithm with other different algorithms in terms of the estimation accuracy. We assess the estimation accuracy by the mean absolute deviation. So this column is the result obtained by our groupInspect algorithm. So we can see that in general, the groupInspect can achieve a better performance than other algorithms. And these 2 columns are the projection-based algorithm for estimating the high-dimensional change points. And in general, we can see that the projection-based algorithm works better than other types of the algorithms. And finally, we look at the result for the multiple change point estimation. So in this simulation study, we also compare our algorithm with the inspect algorithm. So we set the 3 change points at the time 300, 600, and 900. The whole time series has the length of 1,200. We also run the algorithm 100 times, and each time we can get an estimated location from both the groupInspect algorithm and the inspect algorithm. And then we plot all the estimated locations on the histogram. So the left-hand side is the result from the groupInspect algorithm, and the right-hand side is the result from the inspect algorithm. So if we look at the right-hand side here, so inspect algorithm was only able to pick out the change points at time t equals to 600. However, compared to inspect, our groupInspect algorithm was good at picking out all the 3 change points. And also that the groupInspect can estimate more change points than the inspect algorithm, which again suggests that the groupInspect can have a better performance than the inspect algorithm. That's all. Thank you.